Hello, ladies and gentlemen. We're going to do 3.8 and 3.9 today. We're going to be talking about Newton's method and differentials. So our objectives are that we're going to approximate a zero using Newton's method, and then we're going to use a tangent line approximation to find a differential. All right, so let's talk about Newton first. So this is considered Newton's method, and let's kind of talk about visually what it's doing. So let's say I have a function, some random little function that does something like that, except, my bad, I'm going to draw another one. He needs to cross the x-axis. So let's say I have a function that does that. That's better. Alrighty, so this guy's a loser. Okay, so this is going to be my x value, so this is x f of x, right? So then, if I were to draw a tangent line, like that, there's my tangent. In theory, it's not a great example, but this is a zero of my function. And notice that if I take the tangent line at that point, again, crappy picture, but the theory is that the tangent line can be used to approximate a zero of, that's an of, the function. Okay, so that's what we're going to be doing today is we utilize Newton's method. Alrighty, so it's not in the same location, but it is an approximation. Alright, so here's the basic process for Newton's method. The first thing that you want to do is you want to have a zero in an interval, and I need a function that is differentiable. So those are my criteria before I can use Newton's method. And then I'm going to estimate to start a value for x, which is close to c. Okay, so let's say in my particular grapher, this is c, and I'm going to pick a value that's close. I'll write close right there. I'm going to pick a value that's close. So, and this is a great time to use your grapher to help you. And yes, we could use our grapher to find the actual zero, but Newton's method is a way of getting a more precise answer. And then we're going to determine a new approximation using this handy-dandy formula, x sub n plus 1. So remember that when I have n plus 1, that is the new term. So I'm going to write new underneath it so we understand what we're using. So I'm going to take my first term, so I'm going to write old, right? And then I'm going to subtract the function evaluated at the old value, and I'm going to divide it by the derivative at the old value. Okay, so this is the handy-dandy formula that we use for Newton's method. And then I'm going to continue the process until I reach the desired accuracy. All right, so that's what we're going to do for Newton's method. Newton's method is hideously tedious, but it is kind of helpful. So to manage this process, we're going to do an example, and I'm going to put my data in a table. All right, so if I start my example, of course, we're going to use Newton's method to approximate the zeros, or a zero, approximate, I'm going to write a zero instead of the zeros, of f of x is equal to, where's my math? 2x cubed plus x squared minus x plus 1. And then we're going to continue the process until two successive approximations differ by the 0.1231. Alrighty? So as I start this process, the first thing that I'm going to do is I'm just a little bit anal. I'm going to write this down. So 2x cubed plus x squared minus x plus 1. I'm going to take the derivative of that, okay, my tangent line approximation. So 6x squared plus 2x minus 1. And then I'm going to write down the handy-dandy formula. So x of n plus 1 is x sub n minus f of x sub n over f prime of x sub n. Alrighty? And then if I substituted in the values that I have from here, that says that my new term is going to equal wherever we start minus, and then I would have my 2x cubed plus x squared minus x plus 1 over, and then my derivative evaluated at that point, so 6x squared plus 2x minus 1. So sometimes it's really helpful to manage all of this in a table. So n is going to represent, I'm starting to draw my table, which value I'm trying. So here's going to be my first value. And then my next portion of the table is going to be x sub n. And I'm going to leave a lot of room because I have a lot of decimals to manage. And then I'm going to do this in stages. Here's f of x sub n, and then f prime of x sub n. And then the last one is the approximation minus f of x sub n over f prime of x sub n. And remember, when you do this process, this value then becomes my second starting point. So I'm going to just sketch a quick graph. All right, so if I actually put the equation in my grapher and looked at it, it might look something like that. And this 0 is near a negative 1.2. So I'm going to use a negative 1.2 as my first 0. So then I would write my negative 1.2, okay? And then I would run this value through the original function, and I'm not going to bore you with those details. I'm just going to write down the numbers so you can verify later. And this is a 184,123. And remember, since I am finding successive values to the fourth decimal place, it's in my best interest to write down some decimal places. And then if I run this value through the derivative, I get 5.24123. And then if I substitute these three values into this equation, I would get a negative 1.23511. And this value is going to become my second estimation, so 23511. And then I'm going to do that process again. So I'm going to run the new value through the original function, so a negative 0.00771. And then I'm going to run the new values through the derivative, 5.68276. And then I'm going to run the new value through my Newton's method approximation, and I'm going to get a negative 1.23375. And you can see that we're getting closer. So then my next one, this becomes my new number, so negative 1.23375. And it's helpful to know how many iterations, because sometimes you might be asked the equation, how many iterations did you have to do to get to this level of accuracy. So if I do the third one and I run it through the function, I get 0.12341, and then my derivative is 5.66533, and then when I substitute all three of these values into that equation, I get a negative 1.23375, and then this would become my new one. But if you'll notice, I'll use my little pink one, 23375. These guys now match, and we're done. Okay, so then we would say the estimate of the 0 of f is a negative 1.23375. So that was pretty easy. A couple of things that we need to remember or note about Newton's method, and that is, I'm going to write note, it doesn't always work. doesn't always work. So if I found my derivative and then I evaluated it at the point and I got a 0, well, if I look back up here into my equation, if I get a 0 for the derivative, it's not going to work because the world's going to explode, and we don't want that to happen. So Newton's method doesn't always work, but it is a great way to find an approximation of a 0 of a function. Alrighty, there is a handy-dandy program for this, and we will utilize that program in class and then work on it together. So the next section that we're going to do is 3.9, and we're going to be kind of continuing the ideas of Newton's method, and we're going to be doing what's called a tangent line approximation. Alrighty, and we're going to use differentials. So I'm going to draw a diagram. Hopefully it's relatively helpful as we talk about our differentials. So here's going to be my handy dandy graph, and I'm going to have a function, okay? So I'm going to call this my function, f of x. And then at some place along the function, I'm going to have a point, and the value of that point is c, and then of course the y value. So this is c, f of c, and that would be that point right there, okay? If I draw the tangent line at my point, kind of a tangent line, and then I take a value, I'm going to put him right here, and then I pick a corresponding value right there, and I kind of drop down my dotted line. Well, if I call this delta x, because I'm changing my x value, then this is c plus delta x, righty? Then this point right here is going to be the derivative at c plus delta x, right? Because it's on the tangent line. And then this guy up here is going to be c plus delta x and f of c plus delta x. Alrighty? Okay? So then, hopefully that's a little bit clear. So here's a point C, and then I have the y value. And then I drew my tangent line at that point, and then I chose another value over here, so it's c plus delta x, because I just added delta x. Well, because this is the derivative, or the tangent, and this is the derivative evaluated at this point, right? And then this point up here on the graph is c plus delta x, and then this is the y value at the c plus delta x. Alrighty. What other things can I add to our diagram? I think what we want to do is add this. So it's important to notice that this is f of c plus delta x, okay? And then I think that's enough for the time being. So we're going to use our situation here to approximate values on our graph. And then I'm just going to write a little bit more information. I'm going to write x minus c is going to be the change in x, and we're going to call him delta x. And then when delta x is small, then we have the change in y, or we're going to call him delta y. Okay? Alrighty, so then I'm going to write a couple of little equations. If I were to do dy dx, and then I had an equation, I could cross multiply, and I could get that dy is equal to f of c plus delta x minus my f of c, right? And then I'm going to put my delta x out here on the outside edge. And then I'm going to write dy is equal to the derivative evaluated at c and then dx. Okay? So notice that this is where I did my cross multiplication, and I'm just evaluating a little bit differently. Okay, so this is the function at c plus delta x minus this. So we're looking for this little guy right here, the difference between the two graphs. So it's the derivative and then delta x. Alrighty? Okay, so I'm going to write now, better scoot my paper up so you can actually see it, the differential. And the differential is the difference between the two graphs. So this is a differential. And its formal definition is dy is equal to f prime of x dx. And then we're also going to talk about delta y, the change in the y. Okay, so this is the differential. This is the change in y. It's going to be f of x plus delta x minus f of x. Okay, so if I were looking in the change in y, this is the differential. This is going to be the change in y. Alrighty, so let's do an example. And I'm going to draw another little picture once we get started. So the example is going to say let y equal x squared, and I want to find dy when x is 1 and dx is 0.01. So that's telling us that the change in x is going to be 0.01. And I want to compare this value, called the differential, E-N-T-I-A-L, that's a long word, with the change in y for x is equal to 1 and delta x is 0.01. And I know this seems like just some semantics, but we're comparing a differential to the change in y. So let's look at a little graph of it because it might help our little brains. So let's say I have, here's my cute little parabola, this part of it, okay? And here's the point 1 and 1, so it's right there, alrighty? And then if I were to draw my tangent line at that point, there goes my little tangent, okay? Alrighty. So then if I look at my information, this information right here is going to be dy, and this information, if I had another point, my bad, I'm going to scoot this guy over here. I want this dy, and I have this point here. This is delta y. Alright, so let's start doing our math because it's actually, I think, easier to think about the equations. If I have f of x is equal to x squared, and I take the derivative dy dx, I get 2x. Well, if I want to solve for the differential, that guy has to go over there. So I get dy is equal to 2x dx. Okay? Well, then it's pretty easy, and I can just substitute my values in. So dy, here's the 2. I'm going to evaluate. Can you still see that? Yes, you can. At 1, and then my dx is 0.01, and I'm going to get 0.02. So I know that dy, when x is 1 and dx is 0.01, it's going to equal 0.02. Alrighty, but the problem asks us to compare delta y. Okay, so I'm going to say that delta y is equal to f of x plus delta x minus f of x. And if you think about this, this is the numerator of your slope. That's kind of cool. Alrighty, so then I'm going to use all of my values. I know that delta y is going to equal f of 1 plus 0.01 because delta x and dx are the change in x minus the function evaluated at 1. So this is going to be f of 1.01 minus f of 1. So I'm going to get 1.01 quantity squared minus 1 squared, and that tells me that delta y is going to equal 0.0201. Alrighty? So we've calculated both and we can compare. Notice that this is just a wee bit different. And so if I needed to write a statement, I would say the values for delta y and dy will get closer and closer. and they're going to get closer and closer to each other as dx approaches 0. Okay, so I'm saying that these two, dx and delta x, are going to become closer and closer and closer as my delta x, okay, and I'm going to add that to my diagram. There's my little delta x, okay, as delta x goes to 0. So what that's saying is dy and the change in y are going to become almost identical. Alrighty, sometimes we see problems and all they want us to do is find the differential using the given function. So this example says find the differential, and we're almost done, you lucky dogs, differential dy, putting that there just so you know what they're talking about, of the given function. And all of my pens are dying. I need to go shopping. So I'm going to be given y is equal to 9 minus x squared. And because I'm going to be taking a derivative, I like to write this as 9 minus x squared to the half. So then if I start solving the problem, I'm looking for dy, so I could write dy dx is going to equal 1/2 times 9 minus x squared to the negative 1/2 times the derivative of the inside. Gotta love the chain rule. Those two guys go away, and if I rewrite this, this is a negative x over the square root of 9 minus x squared. But remember, I'm solving for the differential, so he has to go over there. So I would write that dy is equal to a negative x over 9 minus x squared dx, and now I have completed all my tasks. So I'm guessing that you might be wondering, where in the heck am I ever going to use this? So here's a thought about an application of this process. Okay, so let's say I know that delta y is f of x plus delta x minus f of x. Industry, manufacturing, lots of industries are very concerned about error. I want to make sure that my product is as reliable or has the least amount of error possible. So we take this equation for delta y, and this is going to be the propagated error. Okay, this is going to be an exact value, and this is going to be the measured value. And so I could calculate, say, how much error is being created in a manufacturing process, because if I can minimize my error, I have a much more reliable product, and then my consumers are happy, I sell more, I make more money. Woohoo! Alrighty, that's it for today. I will see you tomorrow.